Hello, I'm Ryunha Lee from IXL Lab. Today I will present a paper titled Language Models Meet World Models, Embodied Experiences Enhanced Language Models, which was published at NeurIPS 2023. The main topic of this paper is as follows. Recent studies show that large language models can assist decision-making in embodied tasks, demonstrating a certain level of understanding of the physical world. However, large language models like ChatGPT struggle with reasoning and planning in physical environments due to limited robustness. This paper aims to inject fundamental embodied knowledge into pre-trained large language models while retaining their generality. To achieve this, it introduced a novel training paradigm, fine-tuning with embodied experiences from world models. Before delving deeper into proposed training paradigm, it's important to understand what a world model is. A world model refers to embodied simulators that replicate physical interactions in real-world environments, offering a way for models to understand how objects interact with each other and how actions can influence the environment. Essentially, a world model is a simulated environment where a language model agent can interact with objects and perform actions, gaining experience and learning how physical tasks work. In this paper, the author uses Virtual Home, a multi-agent simulator specifically designed for household activities. It contains various objects and their relationships, which are essential for training a large language model to understand the physical world. Actions in this model are simplified into an executable format, which is represented as action. The proposed method, Embodied Experiences from World Models, aims to inject embodied knowledge into language models without sacrificing the generality and language modeling abilities of the model. This approach is further divided into two sub-methods, goal-object-oriented planning and random exploration. The first sub-method, goal-oriented planning, focuses on generating experience by aiming for specific goals. The model collects various activities and defines their corresponding objectives. For example, consider the activity setting of a table. To achieve this, there are several sub-goals such as placing a fork and a plate on the table. The method leverages the Monte Carlo tree search to determine the sequence of actions that should be taken to accomplish these goals. In this process, penalties of -0.1 are applied for each step, while rewards of +2 are given when a goal is successfully completed. The experiences generated during this process are then compiled into data used for plan generation and activity recognition. This approach ensures that the model learns how to organize and execute a sequence of tasks in an environment. The second sub-method, random exploration, is designed to mimic the human learning process of exploration. Multiple agents interact with objects within the world model, and their movements and the final location of the objects they interact with are recorded. These recorded interactions are then transformed into two self-supervision tasks, counting and object path tracking. This allows the model to learn from unsupervised exploration in the environment. For example, from the perspective of a pillow, only the movements of the agent that affect the pillow's position are recorded. The paths taken by agents that do not influence the pillow's position are ignored. Based on these interactions, the pillow's movement path and its final position are stored as experience data. This experience helps the model perform object path tracking, a task where the model must determine the movement path of an object in the world model. To evaluate how well the model trained within the paradigm performs, the authors propose several evaluation tasks designed to assess different abilities of the model. For plan generation ability, the tasks include plan generation evaluation, housework QA, and negation housework QA. In the plan generation evaluation tasks, the model is required to generate a plan for a household activity that it has not seen before. This plans for activities that include unrelated objects in the context. The task is divided into 4 categories: vanilla scene, vanilla unseen, confusing scene, and confusing unseen, based on how familiar the activity is to the model. In the housework QA test, the model must identify the relevant objects needed to complete the household activity. Conversely, the negation housework QA task, the model is asked to identify objects that are irrelevant to the task. Examples of each task are provided into paper to demonstrate the model's capability. For activity recognition ability, 2 tasks are defined: activity recognition QA and activity inference QA. In activity recognition QA, the model must choose the correct activity name based on a given human written plan. On the other hand, in activity inference QA, the model is required to infer the activity name from the final state of the world model. Although the answer to both tasks might be the same, the input to each task is different. One provides a plan for a specific activity, and the other provides the state achieved after completing the activity. For counting ability, the model is tasked with determining the number of objects in a specific location based on a provided sequence of actions. The model must count the objects in a given space after following a series of interactions. For object path tracking ability, the tasks include object path tracking evaluation and object location QA. In the object path tracking evaluation task, the model is required to generate the full movement path of an object. In the object location QA task, the model must determine the object's location before or after it has moved to another position in the environment. The proposed approach was tested on several large language models, including GPT-Neo, GPT-J, and ChatGPT. The results showed that the model trained using the method outperformed the baseline models across all tasks. In fact, the model with the method excels in 7 tasks when compared to ChatGPT. When similar comparisons were made using OPT-13B and Llama-13B, the model trained with the method demonstrated superior performance on 8 tasks compared to ChatGPT. Additionally, the author tested the BABI dataset, which is designed to evaluate multiple types of knowledge and reasoning abilities. The suggested approach outperformed based language models on all tasks except for 2 supporting fact tasks. This highlights the robustness of the approach across a range of tasks designed to test the model's capabilities. Finally, the authors conduct ablation tests to further assess the impact of removing individual training tasks. The results of this study show that removing tasks that are related to similar abilities leads to a decrease in performance on downstream tasks. The most effective training configuration were those that retained all tasks as indicated by the performance in bold in the result table. Thank you for listening my seminar.